Good morning students. Welcome to 11th standard chemistry video class. We are discussing lesson 10 chemical bonding. In our last video class, we completed the topic valence bond theory. In this video, we are to start with the next topic hybridization. Hybridization. Before starting with the definition for hybridization, let me discuss why we have to introduce the topic hybridization. Here, the bonding in simple molecules such as hydrogen molecule, fluorine molecule can be explained on the basis of valence bond theory. But the observed properties of polyatomic molecules such as methane, ammonia, beryllium chloride, etc. cannot be explained on the basis of valence bond theory. For example, structure of methane is tetrahedral and it contains 4 carbon-hydrogen bonds. All the 4 carbon-hydrogen bonds are equivalent. But it is not explained on the basis of valence bond theory or overlap of atomic orbitals of hydrogen and atomic orbitals of carbon, where hydrogen with 1s atomic orbital and carbon with 2s2, 2px2, 2py0, 2pz0 atomic orbitals with different energies. In order to explain these observed facts, Linus Pauling introduced the new topic called hybridization. Here we are having the definition for hybridization. Hybridization is the process of mixing of atomic orbitals of the same atom with comparable energy to form equal number of new equivalent orbitals with same energy. The resultant orbitals are called hybridized orbitals and they possess maximum symmetry and definite orientation in space so as to minimize the force of repulsion between their electrons. Whenever the atomic orbitals of the same atom with comparable energy mixed with each other, it forms equal number of new equivalent orbitals with same energy. The newly formed orbitals are said to be hybridized orbital. Hence, this hybridized orbital possesses maximum symmetry and definite orientation in space so as to minimize the force of repulsion between their electrons. It is an important question. If they ask what is hybridization, you have to give the last 5 lines from the paragraph. Next, let me discuss the types of hybridization and the geometry of molecules. Types of hybridization and the geometry of molecules. Here, we have to discuss sp hybridization, sp2 hybridization, sp3 hybridization and bonding in ethylene molecule and acetylene molecule. First, we will start with sp hybridization. sp hybridization. In order to explain sp hybridization, consider beryllium chloride with the formula BeCl2. Consider the bond formation in beryllium chloride. Here, beryllium with the atomic number 4. The ground state valence shell electronic configuration of beryllium atom is stable electronic configuration of helium 2s2 2p0. In the ground state, the valence shell electronic configuration of beryllium is shown here. 2s orbital with 2 electrons. In 2p orbital, there is no electrons. In beryllium chloride, we are having 2 beryllium chlorine bonds. It is observed that the beryllium chloride is linear. Valence bond theory explains this observed behavior by sp hybridization. In ground state of beryllium, one of the paired electrons in the 2s orbital get excited to 2p orbital, that is in 2px orbital. Now 2s orbital contains one electron and 2px orbital contains one electron. It is shown here. Now the 2s orbital and 2p orbital hybridize and produce two equivalent sp hybridized orbitals. Here these two sp hybridized orbitals contains one electron each. These sp hybridized orbitals have 50% s character and 50% p character. These sp hybridized orbitals are oriented in opposite direction as shown here. Here we are having two chlorine atoms. In chlorine atom, last shell 3pz orbital contains one electron. Hence, the two sp hybridized orbitals of beryllium overlaps linearly with 3pz orbital of the each chlorine to form a covalent bond between beryllium and chlorine. It is shown here. In the left side, one of the sp hybridized orbital of beryllium atom overlaps with 3pz orbital of chlorine atom, forming one covalent bond. In the right side, one of the sp hybridized orbital of beryllium atom overlaps with 3pz orbital of chlorine atom, forming another covalent bond. Here, sharing of electrons takes place between two sp hybridized orbital of beryllium atom and 3pz orbital of two chlorine atoms. Hence, in beryllium chloride, there are two BeCl bonds. This shows the sp hybridization in BeCl2. Next, let me discuss Sp2 hybridization. In order to explain Sp2 hybridization, consider boron trifluoride with the formula BF3. Consider the bond formation in boron trifluoride. Here, boron with atomic number 5. The ground state valence shell electronic configuration of boron atom is stable electronic configuration of helium 2s2 2p1. In the ground state, boron has only one unpaired electron in the valence shell. But here we are having three boron fluorine bonds. In order to form three covalent bonds, three unpaired electrons are required. In order to get three unpaired electrons, one of the paired electrons from 2s orbital is promoted to 2py orbital. It is shown in the excited state of boron atom. Now 2s orbital with one electron, 2px orbital with one electron and 2py orbital with one electron. It is shown here. In boron, one 2s orbital and two 2p orbitals, namely 2px and 2py in the valence shell hybridizes and forms three equivalent sp2 hybridized orbitals. It is shown here. Each sp2 hybridized orbitals contains one electron. Now, these three orbitals lie in the same xy plane and the angle between any two orbitals is equal to 120 degree. Here we are having three fluorine atoms. In each fluorine atom, the last shell 2pz orbital contains one electron. Hence, these three sp2 hybridized orbitals of boron overlaps with each 3pz orbital of the fluorine to form three covalent bonds. This overlap takes place along the axis which is shown here. Here, at an angle of 120 degree, the three sp2 hybridized orbitals are placed. Now, these three sp2 hybridized orbital overlaps with 2pz orbital of three fluorine atoms and forms three covalent bonds. Here, the sharing of electrons takes place between 3 sp2 hybridized orbital of boron atom and 2pz orbital of 3 fluorine atoms. Hence, three covalent bonds are formed between boron and fluorine. This shows the sp2 hybridization in BF3. Next, let me discuss sp3 hybridization. In order to explain sp3 hybridization, consider methane with the formula CH4. Consider the bond formation in methane. Here, carbon atom is bonded with 4 hydrogen atoms. Here, carbon with atomic number 6. The ground state valence electronic configuration of carbon is stable electronic configuration of helium 2s2 2p2. It is also given by 2s2 2px1 2py1 2pz0. In the ground state, carbon has two unpaired electrons in the valence shell, but here we are having 4 carbon hydrogen bonds. In order to form 4 covalent bonds, 4 unpaired electrons are required. In order to get 4 unpaired electrons, one of the paired electrons from 2s orbital is promoted to 2pz orbital. It is shown in the excited state of carbon atom. Now, 2s orbital with 1 electron, 2px orbital with 1 electron, 2py orbital with 1 electron, 2pz orbital with 1 electron. It is shown here. In carbon, 1 2s orbital and 3 2p orbitals hybridizes to form 4 equivalent sp3 hybridized orbitals. Each sp3 hybridized orbital contains 1 electron. The angle between any two sp3 hybridized orbital is 109 degree 28 minutes. Here we are having 4 hydrogen atoms. Each hydrogen atom with 1s1 electronic configuration. Here, these 4 sp3 hybridized orbitals of carbon overlaps with each 1s orbital of hydrogen to form 4 covalent bonds. Hence, the 1s orbital of the 4 hydrogen atoms overlap linearly with 4 sp3 hybridized orbitals of carbon atom to form 4 carbon hydrogen sigma bonds in the methane molecule. Here, sharing of electrons takes place between 4 sp3 hybridized orbital of carbon atom and 1s orbital of 4 hydrogen atoms. Here, 4 covalent bonds are formed between carbon and hydrogen. This shows the sp3 hybridization in CH4. Next, let me discuss bonding in ethylene. Bonding in ethylene can be explained on the basis of hybridization concept. Ethylene with the molecular formula C2H4. The carbon with the atomic number 6. The electronic configuration of valence shell of carbon in ground state is given by stable electronic configuration of helium 2s2 2px1 2py1 Y1 2p is at 0. The valency of carbon is 4. To satisfy the valency of carbon, promote an electron from 2s orbital to 2pz orbital in the excited state. It is shown here. In excited state of carbon, it contains 1 electron in 2s orbital, 1 electron in 2px orbital, 1 electron in 2py orbital, and 1 electron in 2pz orbital. Ethylene contains 2 carbon atoms. Both the carbon atoms undergoes sp2 hybridization involving 2s orbital, 2px orbital, and 2py orbital. Here, one 2s orbital and two 2p orbitals, namely 2px orbital and 2py orbitals, undergoes hybridization and forms 3 equivalent sp2 hybridized orbitals. Each carbon atom forms 3 sp2 hybridized orbitals. Here, each sp2 hybridized orbital contains 1 electron. They are lying in the xy plane at an angle of 120 degree to each other. The unhybridized 2pz orbitals lies perpendicular to the xy plane. That is, the 2pz orbital not involved in hybridization. Now, let me discuss the formation of sigma bond in ethylene molecule. Among the 3 sp2 hybridized orbital, one of the sp2 hybridized orbital of each carbon lying on the x-axis overlaps linearly and forms carbon single bond carbon. The single bond formed between carbon and carbon is sigma bond. Remaining 2 sp2 hybridized orbitals of each carbon atoms linearly overlap with 2 1s orbitals of 2 hydrogen atoms and forms 2 carbon hydrogen sigma bonds. Similarly, next carbon also forms 2 carbon hydrogen sigma bonds. Here we are having 4 carbon hydrogen sigma bonds and 1 carbon-carbon sigma bond. Next, let me discuss the formation of pi bond in ethylene molecule. Here, in both carbon, we are having unhybridized 2pz orbital. Hence, they overlap sideways and forms a pi bond between carbon and carbon. Hence, in ethylene, double bond is formed between 2 carbon atoms. One bond is sigma bond, the next bond is pi bond. It is shown here. Next, let me discuss bonding in acetylene. Similar to ethylene, the bonding in acetylene can also be explained by the concept of hybridization. Acetylene with the molecular formula C2H2. Here, carbon with atomic number 6. The ground state valential electronic configuration of carbon is given by stable electronic configuration of helium 2s2, 2px1, 2py1, 2pz0. The valency of carbon is 4. To satisfy the valency of carbon, one of the electron from 2s orbital is promoted to 2pz orbital in the excited state. In acetylene molecule, both the carbon atoms undergoes sp hybridization involving 2s orbital and 2px orbital. Here, one 2s orbital and one 2p orbital, that is 2px orbital, undergoes hybridization and forms 2 equivalent sp hybridized orbital. Each carbon atom forms 2 sp hybridized orbital. Each sp hybridized orbital contains one electron. The two sp hybridized orbitals lying in the x-axis. The unhybridized 2p y orbital and 2p z orbital lie perpendicular to the x-axis. Now, let me discuss the formation of sigma bonds in acetylene molecule. Among the two sp hybridized orbital, one of the sp hybridized orbital of each carbon lying in the x-axis overlaps linearly and forms carbon single bond carbon. The single bond formed between carbon and carbon is sigma bond. Remaining one sp hybridized orbital of each carbon atom linearly overlap with 1s orbital of one hydrogen atom and forms one carbon hydrogen sigma bond. Similarly, next carbon also forms carbon hydrogen sigma bond. Here we are having two carbon hydrogen sigma bond and one carbon carbon sigma bond. Next, let me discuss the formation of pi bonds in acetylene molecule. Here, in both carbon, we are having unhybridized 2p y orbital and 2p z orbital. Hence, they overlap sideways and forms two pi bonds. Two pi bonds are formed between two carbon atoms. One pi bond is due to sideways overlapping of 2py orbital. The next pi bond is due to the sideways overlapping of 2pz orbital. Here in acetylene, between two carbon atoms, we are having triple bond, in which one is sigma bond and remaining two are pi bonds. It is shown here. Hence, in this video, we completed the topics hybridization, types of hybridization, and the bonding in ethylene molecule and acetylene molecule. All the topics are very important. Let us stop up to this topic. The remaining topics that we will discuss in our next video class. Thank you.